We've been promised helper robots in our homes for what, decades now? So where are they? Well, today we're diving into a really cool breakthrough called MOMAGEN that might just be the key to finally getting robots to tidy up our messy, real-world homes.
And it's a totally fair question, right? We see these incredible robots in labs doing amazing things, but the dream of one just, loading the dishwasher, it's still just a dream. And the reason is pretty simple. The jump from a perfect, predictable lab to your unpredictable living room is absolutely massive.
And this slide right here gets to the heart of it. Think about it. A factory robot might stack the same perfect blocks in the same exact spot a million times over. But a robot in your home, it has to deal with pure chaos, a sock on the floor, a chair that's been moved. It's not about programming one perfect move, it's about teaching it to handle all the endless, messy possibilities of real life.
Okay, so how do we teach them to handle all that chaos? Well, for the most part, it's the same way we learn new things, by watching. It's a method called imitation learning. And while it's a super powerful idea, it comes with one giant bottleneck.
See, to train a robot that's actually useful, you need a mind-boggling amount of data. And that usually means a person has to physically guide the robot, they call it teleoperation, to show it how to do a task, over and over and over again in thousands of slightly different ways. You can just imagine how crazy expensive and time-consuming that gets. It's just not scalable.
All right. So if that wasn't hard enough, let's add another huge layer of difficulty. What happens when the robot isn't just a stationary arm bolted to the floor, but it has wheels and can actually move around your house? This introduces a whole new world of problems. And this comparison really says it all. A static arm, it has its little bubble it can work in. It's predictable. But a mobile robot, it could be anywhere in the room. It has to coordinate its own movement while also coordinating its arms. The complexity doesn't just go up a little bit, it explodes exponentially. And this brings us to the first massive hurdle, and it's called reachability. It sounds simple, but it's absolutely critical. The question is, can the robot park itself in a spot where its arms can actually reach the thing it's supposed to grab? Because if it's off by even a few inches, the whole task fails. Game over before it even starts.
And hurdle number 2 is visibility. Robots learn by seeing, right? So if the cup it needs to pick up is hidden behind the coffee maker, or if the robot just turns its camera away at the wrong second, it's basically flying blind. And you can't teach a robot to pick up something it can't even see.
So let's recap. We've got this huge data problem, and it's made way, way worse by these challenges of mobility, reachability, and visibility. To tackle this, researchers at Stanford and UT Austin came up with a really clever new way to automatically generate training data. It's called MOMAGEN. The big idea behind MOMAGEN is to stop thinking about just replaying the exact same motion over and over. Instead, it thinks about the problem like solving a maze. It understands the goal of the task, and then it figures out tons of different, successful ways to get there, all while following a very clear set of rules.
And a great way to think about these rules is to imagine you're planning a road trip. You've got your hard constraints. These are the non-negotiable, must-follow rules. You can't run out of gas, you can't drive through a building, and the robot's arms must be able to reach the object. Then you have soft constraints. These are more like preferences. It'd be nice to take the scenic route or to avoid traffic. For the robot, a soft rule would be something like try to keep your cameras pointed at your destination the whole time.
So the whole process is just so smart. It starts with just one demo from a human, but then it totally shuffles the scene around. Now here's the key part. Before it even tries to move, it first finds a perfect new starting spot that guarantees it can both see and reach the target. Only after it finds that perfect spot does it then plot the best path to get the job done. It's a system for generating an almost endless supply of successful examples.
And the result of all this intelligent planning isn't just that you get more data, you get smarter data. And, as you might guess, smarter data leads to much, much smarter robots. So, let's check out the results. The researchers themselves put it perfectly. The real win here is diversity, because MOMAGEN is intelligently creating brand new scenarios instead of just replaying old ones. The robot learns how to handle a much, much wider variety of situations it might actually run into in the real world. And this chart, wow, this really shows you the payoff. Just look at this. When they tried to generate new data for a really messy, cluttered table, the old methods failed every single time. A 0% success rate. But MOMAGEN, because it's smart enough to reposition the robot first, it created a successful example 64% of the time. That's the difference between having zero usable data and having a whole dataset to learn from.
And remember that soft rule about visibility? The one that's just a preference? Well, without it, the robot was basically navigating blind half the time, only seeing its target 46% of the way. But by just adding that simple preference to keep your eyes on the prize, that number shot up to 89%. That nearly doubles the amount of useful, high-quality visual data the robot gets to learn from. So, okay, MOMAGEN is amazing at generating tons of high-quality data in a computer simulation. But here's the million-dollar question. Does any of this actually make a real robot perform better in the real world? And the answer is a huge, resounding yes. Get this. After training a robot on thousands of MOMAGEN's virtual demonstrations, the researchers found they only needed about 40, that's 40 real-world demonstrations to fine-tune it. That is a massive, massive leap in efficiency. And this right here, this is the ultimate proof. If you just tried to train a real robot with those few real-world examples, its success rate was 0, a complete and total failure. But by first training it on all of MOMAGEN's virtual data, that success rate jumped to 60%. That simulation wasn't just practice, it was the essential foundation that made learning in the real world even possible.
And that's really the big takeaway here. What MOMAGEN shows us is that the fastest path to getting capable, real-world robots might not be through millions of hours of expensive manual training. It might actually be through creating smarter, more diverse, and more realistic virtual playgrounds for them to learn in first. It's a real game changer.
Innovations like this mean that day is getting closer than ever. Which, leaves us with one final fun question to think about. When these robots do finally arrive, what is the very first chore you are going to make them do? Thanks for joining this explainer.